And so that's it. So our speaker today is Dr. Scott Chambers, who is a laboratory fellow and technical group leader at Pacific Northwest National Laboratory, also known as PNNL. And he's an affiliate professor of chemistry and material science at the University of Washington, even though the University of Washington is a long, long way for PNNL. That's got to be a long commute. His training is in chemical physics and physical chemistry, but his research over the bulk of his career has been in materials chemistry and physics. And he is one of the foremost experts in photoelectron spectroscopy. And with that, I will turn it over to you for your presentation.
All right.
And again, let me add, remember, ask questions in the chat window if you have any, and I'll interrupt if it's a good time. All right, go ahead.
Well, thank you, Jeff. Appreciate the invitation and looking forward to this time with you. And so my title is shown up there, XPS, a rich source of more than just chemical information. So let me start by telling you how I use XPS and in what scientific context. In my group, we do material synthesis by molecular beam epitaxy, and we are interested primarily in complex oxides of various kinds. And so we have a number of different MBE systems to do different kinds of things. And this is our workhorse for oxides right now. And so it's got a number of effusion cells and electron beam evaporators for metals. And then it has a couple different oxygen sources we can plug in. And here's a cute little artist's conception of the MBE process going on, where you have the individual atoms and molecules, in this case ozone, coming up from the sources below onto a substrate. The substrate's hot, you nucleate, you can make a new material literally one atomic layer at a time. The way XPS figures into this is that we have, coupled to our MBE chambers, we have photoemission chambers, and in this particular case, this is the one that's coupled to this MBE chamber. And so it has two different light sources on it, a monochromatic aluminum K alpha X-ray source, and then a monochromatic helium-1 or helium-2 vacuum ultraviolet source. And we find that of all the tools that you could have hooked up to an MBE system, we think that XPS and UPS, that combination, is probably the most versatile and useful tool that you can have on an MBE system, and that's why we do it. So we can get data on crystalline films that are freshly grown, they haven't gotten dirty yet, and therefore we can really capture them in their pristine state. Well, what I'm going to do today is I'll start off with a little bit of history behind the technique, and then I want to spend the bulk of the time talking about 5 main physical factors that determine what a line shape and a binding energy are for a given element in a given orbital. And then I'll finish with a recent research example having to do with a very unexpected result, where we found that a high mobility two-dimensional whole gas forms at the interface of niobium-doped strontium titanate and undoped silicon. Completely unexpected result that baffled us for a long time, but with XPS, we were able to figure out what it means and why it's happening. So XPS as a technique has a long and storied history. Goes all the way back to Heinrich Hertz back in the 1800s with the photoelectric effect. He, of course, shined UV light on a metal plate in a vacuum and had a potential on it and was able to draw current away. He tried to explain his data with his classical understanding of light, and it didn't work. He could explain some aspects of his results, but not all of them. And it wasn't until 1905 that Albert Einstein provided a more satisfactory explanation based on the concept of photons. And for this, he eventually won the Nobel Prize in 1921. Then a few years later, after that explanation, Ennis actually got the first XPS spectra using a Röntgen X-ray tube. And then not much happened, but if we fast forward to the 1950s, Kai Sigban, University of Uppsala in Sweden, built the first magnetic spectrometer to do actual XPS. And from then, the technique really took off in a number of different research labs. Dave Shirley's lab at Berkeley was one of the most prolific labs in terms of helping to develop the technique and understand it. And then a few years after that, Kai Sigban actually received the Nobel Prize in Physics for his development of XPS as a powerful tool for material science. And then since that time, the technique has proliferated, and it is literally found everywhere. It's hard to go to any research facility, whether it be a university or a national lab or an industrial lab, where you don't find XPS. The problem is that a significant number of practitioners don't really understand the technique. And this is something that seems to be self-perpetuating. And so I want to try to address that and show why that is. And probably the main reason people don't understand the technique is they don't understand that photoemission is not a one-electron process. Now, we get the impression that it is because we see pictures like this. We see an atomic orbital on an atom, it absorbs an X-ray, and out comes an electron. And then the way that conservation of energy relationship is usually expressed, which is a very useful formula, this one, which relates the X-ray energy to the measured kinetic energy of the outgoing photoelectron, and then its binding energy in the solid, and there's a correction for the work function of the analyzer. But that equation really leads to a one-electron paradigm. You'd have one orbital on one atom, you send in one X-ray, and out comes one electron. Boom. But that's not really what happens physically. We are far better off if we recognize that what the X-ray really does is it takes an n-electron atom and it transitions it to an n-1 electron ion and a photoelectron. And if you then combine those two equations, you end up with this formula for the binding energy. It's the energy difference between the n-1 electron ion that you have after core level photoemission and the n-electron atom that you had before. And the reason that this is really important is because the wave functions of those n-1 electrons in the core ionized species are quite different than the same orbital wave functions were for the atom prior to photoemission. So it's really very important, I think, that we understand that all of the electrons in the atom are involved at some level, and in some cases more than others, depending on the element. Okay, so here's a typical spectrum, and if you've done any XPS, this looks very familiar, but what you see is you see different elements, and you see different orbitals giving peaks at different energies, and this is for niobium-doped strontium titanate single crystal, and it's clean, the surface is clean, and so any given element on the periodic chart will have a characteristic set of photoemission peaks for its different orbital energies, and it's like a fingerprint, and that's very useful, obviously. But if we want to go further and know more than just what elements are there, then we need to understand the line shapes. And so there are really 5 different drivers for binding energies and line shapes. And what they are, first of all, the best known one is that of charge distribution or chemical environment. This is the one that pretty much everybody knows about. But another one that hardly anybody knows about is total electrostatic potential. And this can vary in semiconductors in some very big ways. And I'll talk about that toward the end of the talk. Then there's a phenomenon called spin-orbit coupling, which happens whenever you photoionize from any atomic orbital that has an orbital angular momentum of greater than 0, so anything other than s orbitals. There is angular momentum coupling, and this is very important in atoms that have unpaired valence electrons. And then there is valence electron redistribution, which is sometimes called shake-up or shake-off or shake-down, shake phenomena. So what I want to do for the bulk of the talk is to go through and describe each of these and give an example of it and show how it has an impact. So we'll start with the best known one, which is charge distributions or chemical bonding. Oh, sorry, before I get to that, it's worth asking the question for these 5 different effects, are they primarily a function of the atom that photoemits prior to photoemitting, or are they dependent upon the state of the atom after photoemitting? Well, let's take a look. For charge distributions, that is definitely what we would call an initial state effect. It depends on the distribution of electrons in the material prior to photoemission. Total electrostatic potential, same thing. Spin-orbit coupling actually is somewhat controversial. It's not, you can argue either way for it being an initial or a final state effect, and I won't get into that today. Angular momentum coupling is very definitely a final state effect, as is valence electron redistribution. Okay, so now let's talk about these one at a time. Let's start with chemical environment. The reason chemical environment is important is because for any atom on the periodic chart, if you take a look at a plot of the different wave functions atomic wave functions as a function of distance from the nucleus, what you find, and these are just for hydrogen, just to keep it simple, but the outer orbitals, in this case, the n equals 2 and n equals 3 orbitals, they have amplitude in where the n equals 1 orbital also has amplitude. In other words, if you want to put it one way, you could say that the nuclear charge that's felt by the inner core electrons is actually reduced relative to the true value because there is a non-zero charge density of the valence electrons in the core region. And that happens for all orbitals. Another way you could say that is that the nuclear charge that is felt by the core electrons is screened by the valence electrons. So if you have a change in bonding that results in a change in the valence electron distribution around the photo-emitting atom, and let's say for sake of argument that this change in bonding pulls valence electrons away from the atom, that'll reduce the screening and it'll result in an increase in the deep core level binding energy. And the classic example of this are the oxides of silicon grown on a clean silicon wafer. So this is a classic study that was done years ago, but the basic idea is the following. Silicon in its elemental form, of course, is sp3 hybridized bonds to other silicon atoms, very much covalent. Well, if you think about going from elemental silicon to an oxide of silicon, and let's go all the way to SiO2, now all of the nearest neighbors to a given silicon atom are oxygens. And those oxygens are more electronegative than silicon, and so they're going to pull valence electrons away from the silicon. And so the core electrons are going to experience a larger nuclear potential that's going to increase their binding energy. And so if you take a look at this classic study by Franz Himsel, formerly at IBM, what you find is that for light oxidations of silicon, looking at the silicon 2p3 halves peak, which has a binding energy of about 100 eV, you see 4 different peaks there corresponding to the 3 different suboxides of silicon, and then finally SiO2. And so as the formal charge on the silicon goes up, you can see that the binding energy goes up, roughly 1 electron volt at a per unit change in oxidation state. So this is what everybody understands, and everybody uses this primarily to interpret their data. However, this is not the only driver. And I want to illustrate this and actually drive the point home by looking at some spectra for titanium. So I'm going to show you 4 different materials, and we're going to look at the titanium 2p spectrum. We'll start with a thin polycrystalline clean metal that was grown in the same chamber as the photoemission that was done in. And so there's the spectrum. Well, you notice it has 2 peaks, not 1, and that's because of another effect that's very important, and that is spin-orbit coupling. So we'll introduce that now. And so spin-orbit coupling happens because the orbital angular momentum of a core electron and a spin angular momentum of that same electron can couple either parallel or anti-parallel. So here's the parallel arrangement, and here's the anti-parallel arrangement, and they have different energies. The parallel arrangement is rather unfavorable because of this is a relativistic effect, and so this state where you have L plus S for the J total angular momentum, this one is going to be of lower binding energy. Whereas if you have the anti-parallel arrangement where you have L minus S, this is more favorable. It'll have a higher binding energy. So in this case, of course, L is equal to 1 and S is equal to 1/2. So we have J equal 1/2, which is the higher binding energy peak, and we have J equals 3/2, which is the lower binding energy peak. So that's spin-orbit coupling, and it's always there. Now let's go from this titanium 0 containing material to strontium titanate, which is titanium 4. See, we've got a big shift to higher binding energy, and of course that's the chemical shift. We've had nearly 6-volt change in binding energy for the 2p3 halves peak because we've gone from titanium 0 to titanium 4. So that makes good sense. But now let's take a look at a couple of other spectra. Let's take a look at that one and that one. And I'm not going to tell you what they're from at first. Okay, if you were doing surface analysis and somebody asked you to analyze their material and they showed you these spectra, or you measured these spectra, what you might do, and in fact what a lot of people would do, is they would say, oh my goodness, there's all kinds of titanium valences there. Maybe we could do that. Maybe we could fit it to a mixture of titanium 1, 2, 3, 4, and maybe even titanium 5. Who knows? Okay, and in this one, maybe it's a mixture of titanium 2, 3, and 4. Well, if that's what you did, you would be completely wrong, because the blue spectrum is from a cleaved single crystal, ultra-high vacuum cleaved single crystal of Ti2O3. It has 100% titanium 3 plus, formerly titanium 3 plus. The red spectrum is from an epitaxial film of lanthanum titanate, grown in situ with the photoemission chamber, in this case over in Germany at Bessie. This also has nothing but titanium 3, but the spectra are completely different. And so clearly, just because the formal charge is the same does not mean the spectra are going to be the same, because these other effects kick in. And in this case, we have different crystalline structures, different electronic structures, and this gives rise to different final state effects in XPS that completely change the spectra. That's why it's really essential that we understand these different effects if we're going to use XPS intelligently. Okay, let me stop and see if there's any questions at this point. Anything coming into the chat?
Nothing yet. Nothing yet. So
All
go
right.
ahead and keep going.
Okay.
Oh, actually, though, could I clarify one thing?
Sure.
So, since you mentioned this is titanium 2p, that was actually the silicon 2p, correct? And so that had the the silicon 2p 1/2 spin orbit component numerically removed from that data, correct?
Exactly. Yeah, I should have mentioned.
So that should be clear. So the silicon 2p is just like the titanium 2p in that regard. It has the spin orbit coupling. But okay, go ahead.
Yeah, just to point out the spin orbit splitting between the 2p 3/2 and 2p 1/2 in silicon is only about, I think it's something like 5/10 or 6/10 of an EV, compared to here where it's several EV. So it's easier to spot here. Okay. So now let's talk about angular momentum coupling, and this happens in open shell systems, meaning systems that have unpaired electrons in their valence band. So the definition of this phenomena is it's the coupling of the angular momentum of the remaining electron in the core ionized orbital with the angular momenta in the unpaired electrons in the valence band. So let's suppose we have a generic material AB, and this could be an oxide or a nitride or a chalcogenide, pretty much anything where you have elements that have somewhat different electronegativities. Okay. And so there's your electronic structure. And let's suppose we now core ionize the 3s electron. So now that one's gone. Now, if you look at the final state of the ion here, we have 5 unpaired d electrons in the 3d orbital and 1 unpaired s electron in the core. And there are different ways for those angular momenta to couple. And so we're going to get different final states depending on how those angular momenta couple to give the total angular momentum of the system. And for every different way of coupling those angular momenta, you're going to get a different final state. Many of them will be very close in energy, but some of them will be further in energy. Okay? So let's take a look at an example that's probably the easiest one to understand, and that is the manganese 3s spectrum in MnO. Okay, there's a spectrum. It's got 2 peaks, and it has 2 peaks not because there's 2 different oxidation states of manganese present. That's not the right answer. It's all manganese 2 plus, but it's because of angular momentum coupling. So in the valence band, because of the fact that we have octahedral coordination of the oxygens, the crystal field splitting kicks in, and the T2Gs are lower in energy than the EGs for the manganese d orbitals in the valence band. And so in order to think about how this might play out in photoemission, we need to think about angular momentum coupling schemes. And it turns out that for manganese, because of its atomic number, the best way to do this is to use Russell-Saunders coupling. And so in Russell-Saunders coupling, we talk about a term symbol that defines the net angular momentum of the whole system. And it is given by 2s plus 1, where s is the total spin angular momentum for all the electrons. L is the total angular momentum for all the electrons, and then J is just the total angular momentum spin plus orbital. So what we do is we simply recognize that the orbital angular momenta and the spin angular momenta for the individual electrons in the valence band all sum to give a total L and a total S. And then once you have those, then you add those together to get a total J, the total angular momentum. So when we then think about the photoemission piece of it, the total angular momentum of the entire system, the ion after photoemitting from the core, is going to be the angular momentum of the remaining core electron coupled to the total angular momentum of the valence electrons. So it turns out that if you have a high spin crystal field split ground state for an octahedral coordination like this, there's only one way to couple those 5 unpaired electrons, and the term symbol is sextet S, 6s. So how do we get that? Well, it's pretty simple, really. First of all, let's get the total orbital angular momentum. And we're going to start with the projection quantum number for the total angular momentum. That's just going to be the sum of the m sub little l's for each electron. And since we have 1 electron in each suborbital, they sum to 0. And so the total orbital angular momentum of this d state is actually, it's an s state, meaning 0 orbital angular momentum. At the same time, the total spin angular momentum, we have 5 unpaired electrons, all pointing the same way, high spin. So the total spin angular momentum quantum number, the projection quantum number is 5 halves. And S then, because they're all parallel, is also 5 halves. So 2s plus 1 then is 6. And that's how we get the sextet S for the valence band. Now let's think about coupling that sextet S for the valence band with the remaining 3s electron after photoemission. Well, we can either photoionize the spin up or the spin down electron in the 3s orbital, and the remaining electron then is going to have a J of 1/2, and the projection can be either 1/2 or minus 1/2, and that's going to couple with our sextet S, which is the 5 unpaired d electrons. Well, that's basically, let's think then about the total orbital angular momentum of the whole system. It's going to be the remaining 3s electron plus the valence band. And since everything is S-like, then the sum is going to be S-like, so it's only going to be S states for the orbital angular momentum. The total spin is either going to be 5 halves plus 1/2 or 5 halves minus 1/2, depending on whether the spins in the valence band couple parallel or anti-parallel to the one in the core. So that means that 2s plus 1 then is either going to be 7 or 5. So we expect 2 peaks in this spectrum, a heptet S and a quintet S. And we see that our 2 peaks are there, and the correct assignment is that the heptet S is the lower peak and the quintet S is the higher peak. And the reason for that is because the heptet S has a lower binding energy because of the parallel spin alignment. It's less stable. And you can also tell because of the relative intensities, which one has 2s plus 1 equals 7 and 2s plus 1 equals 5. There's a simple theorem of quantum mechanics that says that the energy difference in a system like this should go as the exchange interaction between the core ionized orbital and the valence orbital. And so that's called the Van Vleck theorem, and that number for the 3s orbital on manganese and the 3d orbital on manganese is about 5.6 eV, which is very close to what we measure. So this is an example of angular momentum coupling. Okay, are we good with that? Any questions on that before I move on?
So far, so good.
All righty. Okay, now let's talk about valence electron redistribution or shakeup. So what this is it's a valence shell excitation that occurs as the absorbing atom responds to the perturbation caused by core level photoemission. So when you knock out a core electron, that's a huge perturbation to the system. And the system basically responds to that. And the way it responds is shown here. We'll take our same scenario. We have our material AB, and we're going to ionize, in this case, a 1s electron. And one final state of the ion we can get has just the core hole, as shown here, with all the other electrons having relaxed toward that core hole, but they're staying in their same orbitals. But they've all relaxed toward the core hole. You might call that the ground state of the ion. But it turns out there's a non-zero probability that in addition to having that happen, you can have other ground states of the ion where you get charge transfer. For instance, we could have charge transfer from the green to the red, have a charge transfer event like that. This is a different final state of the ion than the one I just showed you. Or we could have charge transfer from the red to the green, like that. And that is yet a different final state of the ion. And there are lots of different final states of the ion here, depending on how many of these events have some non-zero probability. And so, as an example, let's compare cerium metal. So there's cerium metal, and this is the 3D peak. So there's the spin orbit split, 3D 5/2 and 3/2. And then there's some weak features to the higher binding energy side. Those are probably energy loss features in the metal. But then if we look at cerium dioxide, CEO2, notice how different the spectrum is. Yes, peaks have been moved to higher binding energy, as you would expect, because we're going from cerium 0 to cerium 4. But now instead of having 2 peaks, we have 6 peaks, okay? And it turns out that cerium 4 formally has no unpaired valence electrons, okay, because it's 4f0, 5d0. And so angular momentum coupling is not going to happen because there's no unpaired d electrons. So all of these 6 different features are due to shakeup. And again, if you didn't know that, you might go trying to assign oxidation states to all these peaks, and you'd be completely wrong, and you would have missed the physics altogether. Okay, now I want to come back to the TI-203 and take this very gory looking spectrum in blue here. And what can you do with that? How can you understand that in terms of the combined effect of angular momentum coupling and shakeup? Well, I worked with Paul Bagas at University of North Texas, who's in my view, the leading theorist on photoemission line shapes in the world. And he has a wonderful relativistic Hartree-Fock code, and he calculated what this line shape should look like. And it took quite a long time. And what he ended up with is shown here in red. And as you can see, there are basically 6 peaks in the shakeup spectrum, and his calculations got 4 of them really well. And if we zoom in on that calculation, what you see here are, first of all, the black is the net spectrum, but then below that, you see all the little colored curves. Those are all the individual different final states that had some intensity in his calculations. There are 320 of them. 213 happen at the higher binding energy end, and most of those are shake-up type phenomena. Each of them is extremely weak, but when you have 213 of them, they add up to give you what you see in black. And then the other 107 are shown there, and it's the same thing. Each one of them is pretty weak, but when you add them up, you get what's shown in black. Now, why did the calculation miss these 2? Well, our best hunch is that because these features come from another kind of relaxation phenomena that happens in anything that's got a partially filled conduction band, which TI-203 does. And it's called being a well-screened final state. And what happens here is that conduction band electrons screen the core hole and stabilize in that particular atom, they stabilize the core hole, and so they come in at a lower binding energy. And the reason that we didn't get it with these calculations is because Paul used an embedded atom approach where he had one quantum mechanical cluster, a TI-06 cluster, shown there in the middle, and blue is the titanium. And then he had a bunch of other ions at the appropriate places in the lattice, but they were treated classically. And if you only have one metal atom being treated quantum mechanically, you can't have a conduction band. And therefore, there's no conduction band to screen the core hole. And that's why we didn't get these in the calculation. He tried doubling the size of the quantum mechanical cluster. That didn't do it either. And then because the calculation was now getting so expensive in terms of CPU time, we quit. But we think that that's what's going on. But I hope this conveys that the level of difficulty that you have when you try to interpret these properly. And for many of us, the best thing to do is just to be aware that these kinds of things go on. And so don't interpret these peaks in terms of different oxidation states. All right, you still with me? Any questions to this point?
Still going good. That is a really impressive calculation, I have to say, though. That it's hard with these things that are really inherently many body effects.
Well, the thing I really like about Paul's approach is there's no adjustable parameters, aka fudge factors.
Yeah, that's always good too.
You can see some spectacularly good simulations of photoemission spectra in the literature, and then when you read the fine print in the paper, you realize there's all kinds of adjustable parameters. And, yeah, sure, you can get a perfect fit. You've got adjustable parameters.
No, definitely.
Calculations. It's all ab initio.
Yeah, what almost surprises me more is not these somewhat unusual cases, but the fact that there aren't more of them, and that is remarkably fortunate for most of the people doing XPS.
Yes, indeed. Yeah, this is probably the most bizarre. This is one of the most extreme cases I've ever seen in terms of those two spectra in the middle, the blue one and the red one, being so different for nominally the same valence. That's probably, that one takes the cake.
So we have a question. How long did it take to do the calculations?
Actual CPU time, I don't know. In terms of total thinking time from beginning to end, it was months. He tried it at several different levels of approximation. He started off with just angular momentum coupling, and then he went to single charge transfer events, and then he went to double charge transfer events, and then he put it all together. And the third or fourth set of calculations is the one I'm showing you here. So it was quite a long, many month long investigation to try to figure this out. But I would highly recommend his papers, because he has now done these calculations for a number of different transition metal compounds, and I think it really does shed a lot of light on what's going on with these things.
Definitely.
All righty. One other thing about shakeup: it can happen in metals in addition to oxides. And so here are 4 different transition metal 2p spectra. You notice that all of them have a little asymmetry on the high binding energy side of each spin orbit peak. And the reason that's there is because these are metals, and so you have a partially filled conduction band. And so you can have these many body excitations in the final state, but you have a continuum of possibilities. And I show that schematically here. Because you've got unoccupied states in a continuum above the Fermi level, you can pump electrons up to those different unoccupied states over a range of energies. And so instead of getting a discrete feature some EV away, you just get a manifold of features all on the low kinetic energy or high binding energy side, and that makes the peak look asymmetric, as you see here. Okay, last effect before we get to some examples is total electrostatic potential, another initial state effect. Okay, if you take any solid that you like and think about what does the potential, electric potential, look like as a function of distance through that solid, this is what you would get. And this happens to be for strontium titanate again. So this is a quantum mechanical cluster, and these are DFT calculations of that my colleague Peter Shushko did here at PNNL. And this is the potential as a function of z coordinate through the material. And so clearly, as you go from one atomic plane to an interstitial plane to another atomic plane, the potential changes a lot, but we can define an average potential throughout. And the point here is that anything that changes that electrostatic potential is going to change the binding energy of photoemission peaks from that material. And to illustrate this, if we have, let's take a semiconducting material or a metallic material, anything that doesn't charge up in photoemission. So we'll take the oxygen 1s on niobium doped strontium titanate, which is an N-type semiconductor. Okay, as properly grounded, you measure about 530 EV. Well, in my spectrometer, I can float the sample. I can put a bias on the sample. And so let's suppose I put a 5-volt bias on the sample. That moves all the peaks up 5 EV higher in binding energy, or in this case, 5 EV lower in kinetic energy. And that's because I have now changed the electrostatic potential of the entire crystal, and the peaks move accordingly. Well, you might say, okay, well, that's great, but so what? Well, the point is that in semiconducting materials, depending on the electronic structure, there can be natural internal intrinsic forces that change the electrostatic potential. For instance, band bending in semiconductors. Okay, let's take an N-type semiconductor as an example here. And let's just suppose that you have some acceptor states on the surface. Well, those things can grab electrons from the subsurface region and charge up and leaving behind a positive space charge region down to some depth d, and that's going to cause all the electron orbitals energies to shift up. Conduction band, valence band, and the cores are all going to move up. And then if you bring two semiconductors together to make a heterojunction, then you can have discontinuous changes in the valence band maximum or the conduction band and the conduction band minimum. These are called band offsets. And this is obviously going to make for a big change in the potential within the material as you go from material 1 to material 2. And as you can see here, if we just think about bringing these two materials together, we have different Fermi level positions. And so the Fermi level is going to equilibrate, which means electrons will go from material 1 to material 2. By the time that happens, we're going to have something very complicated like that. So as you march through that material in the direction toward the surface, you can see that the potential is changing. As you move through, the potential is changing a lot. That's obviously going to have a big effect on core level binding energies and line shapes. To show you how that works, let's just go back to the band bending of a single semiconductor as an example. Well, we can set up and solve Poisson's equation for a freestanding semiconductor like that. And so if we do that, and I've picked, somewhat arbitrarily, I've picked a bulk doping density of 2 × 10⁻21 cubic centimeters, a band bending of half a volt, and a dielectric constant of 30. And I can calculate what the potential is going to be as a function of distance from the surface, and that's shown here in red. Okay? Well, let's suppose that I'm measuring this very surface with photoemission. What am I going to get? Well, I'm going to have one binding energy right at the surface. And so if I have a nice sharp core level, it's going to give me a binding energy that is somewhat low because the bands are bending up. And relative to 0, it's going to be about a half a volt lower in binding energy relative to the bulk Fermi level. If I go down one layer, I'm going to get a slightly lower binding energy. The intensity will also be lower because it's attenuated, because it's a little bit deeper. And same thing with the third and the fourth and so on, down to until I reach the bottom of the valence, or the bottom of the depletion width. Okay, so down at x = d, the deepest level in this material is going to have the lowest. There's actually the highest binding energy, and also if my depletion width is smaller than my probe depth, then I'm going to also see some layers that are below the bottom of the depletion width. So we'll have a bunch more peaks that do not change in binding energy because they're below the depletion width. But then I'm going to have all those different contributions to my measured spectrum. My measured spectrum then is going to have a different binding energy, a different width, and a slightly different line shape because of this band bending. But the exciting part of this is if I measure that spectrum, which is simulated by this sum, it is possible to back out the contributions from all the different layers that contribute to it, and that would give you a built-in measure of the band bending. And that's cool, because that's a very useful thing to know for semiconductor systems. So let me give you one simple example, and this is a PN semiconductor heterojunction. It involves a complex oxide.
To clarify real quick,
yeah.
You are including attenuation in that.
Yes, that's why you see as you go from the surface layer to deeper layers, each peak is a little bit weaker than the one above it. Right?
I just wanted to make that clear.
Yeah, absolutely. All right, so we're going to start with lanthanum ferrite, and we're going to alloy 12% strontium onto the lanthanum site. And we're going to grow, that's a p-type semiconductor, it turns out, and we're growing it on an n-type semiconductor substrate, strontium titanate. Okay, here are the spectra. And notice, there's some interesting things. On the oxygen 1s, you have 2 peaks, right? That's because you have oxygen in 2 different materials that have different electrostatic potentials. The lower binding energy feature is the oxygens in the STO substrate. The higher binding energy feature is the oxygens in the LSFO. If you look at the titanium, same thing. then the reason for this is there's a little bit of intermixing at the interface. Some of the titanium from the substrate goes out and occupies iron sites in the film. And so you have, in addition to the substrate feature, which is the larger one, you have a second feature, which is titanium out in the LSFO. In the case of the strontium, you have strontium in both materials. So you have one strontium 3d 5 halves in the STO at one binding energy, and you have a different strontium 3d binding energy for strontium out in the film. And notice that for the materials that are in the film, notice that the binding energy is changing. The binding energy shift relative to the substrate is going up with thickness, because this is 3, 6, 3, 5, and 9 unit cells. In the case of the iron 2p, it's really complicated, because for every strontium that goes into the material and replaces a lanthanum, then one of the irons goes from formally 3+ to formally 4+. So you have a mix of iron 3 and iron 4, making for a horribly complicated spectrum. We're not going to even play with that. But if you look over here on the other side to the lanthanum, notice that there is a different line shape for the lanthanum for the 3 different thicknesses. And you can tell that by the valley between the 2 different features in the lanthanum 4D. So what's up with that? Well, that suggests that there's a built-in potential. There's band bending, if you will, in the LSFO. And we can find out what that band bending is by doing what we had on the previous slide, 2 slides ago. Go ahead and taking a flat band spectrum that we get for a reference sample that doesn't have any band bending, assigning that to each of the layers, then varying the spacing, the energy between those layers, and trying to fit the spectrum. And if we do that for the 3 different film thicknesses, which is shown here, then we can construct the entire band diagram for the whole thing. And that is, as far as I know, high quality core level photoemission data is the only way to get this kind of detailed information on what we call band edge profiles. All right. Any questions so far?
I guess, let me ask, how can you be sure that the one material has no band bending? Because you could have a band bending just from the surface of the material.
Right, that's a great question. I didn't show it, but if you look at the titanium 2p spectra, sorry, can't do that. If you look at the strontium 3D spectra, let me back up a minute. If you look at the strontium 3D spectra and you strip away the component that is from the LSFO, and then compare the line shapes for the different thicknesses of LSFO on there, what you find is that line shape is identical to what you measure for flat band STO. Yeah. So that's how we know there's no band bending in the STO.
Okay.
All right, so let me then end with the kind of the research example. And so now we're going to use XPS to try to understand this whole gas that forms at the interface between niobium-doped STO and intrinsic silicon. This was, by the way, I should say, a completely unexpected result. This was a baseline experiment. We didn't expect anything to happen. But when we grew these films, and this is in collaboration with Professor Joe Nye at UT Arlington, University of Texas at Arlington. So if you take a look at the sheet resistance versus temperature for these, for different mole fractions of niobium, you get a really weird result, and that is this precipitous drop right around room temperature. If you then do Hall measurements to measure the transport, you find that as you go from below room temperature to above room temperature, the Hall coefficient goes from negative to positive, which indicates that the dominant carrier is going from electrons to holes. And so below room temperature, the dominant carrier is electrons in the SNTO, and above room temperature, it's holes. If you then analyze the Hall data to extract the electron mobility, you find that the electron mobility is up around 500 or 600 centimeters squared per volt second. That can't possibly be in the STO because the mobility is probably 1,000 times too high or more, because hole mobility in STO sucks. It's extremely low. So this indicates that there is a hole gas forming in the silicon. So what in the heck is going on? Well, we decided to try to probe this. Because it happens with thicker films and not with thinner films, like 12 nanometers in this case, conventional XPS is useless because we can't see the interface. So what we did is we took the samples and we went to diamond light source and we measured hard X-ray XPS on these samples. And so here's what we learned. We did the experiments with a X-ray energy of 6,000 EV. And so here I show you 3 different materials, plain, just undoped STO on silicon, 20% niobium doped STO on silicon, and then reference flat band specimens of either pure STO with a little bit niobium or silicon. Now, notice, first of all, that in the case of the titanium 2P spectra, you have a whole bunch of structure on the low binding energy side for the films on silicon that you do not see on bulk STO shown in green at the bottom. This indicates a range of valences, 3, 2, 1, and 0. If you take a look at the niobium, you see the same thing. You see a bunch of intensity on the low binding energy side that indicates reduced valences. Okay. Also, you notice that there is a asymmetry on the high binding energy side of all the film peaks, and there is an asymmetric shoulder on the low binding energy side of the silicon. Okay, well, what are you to conclude about this? Well, what you would conclude if you didn't think outside the box on your data, you would conclude that you have multiple suboxides, which explains the reduced valence on the niobium and the titanium. You would conclude that you had an interfacial silicide because that low binding energy shoulder on the silicon 2P is just at the right binding energy to be titanium silicide. And you would conclude that the asymmetries on the high binding energy sides of the film peaks is due to shakeup, and therefore you have a metallic phase. So in other words, you have a polycrystalline metallic mess. But that's not at all what the material is. The material is, by all measures, X-ray diffraction, TEM, everything you can do. It is a very high quality epitaxial film that makes an atomically abrupt crystalline interface to the silicon. So what in the heck is going on? Well, we finally asked the question, could these weird core level line shapes be indicative of large built-in potentials that have something to do with the whole gas formation? If we take a look at what the transport data suggest about the way the band energies vary with depth, they suggest something like this. So we formed a couple hypotheses. One, could the asymmetries be caused by built-in potentials that are big enough to drive the silicon whole gas formation, and also something which is called surface depletion on the STO? Because I didn't show you this in the transport data, but there is indication that the band bending at the surface of the STO is high enough that you actually have a depleted region right at the surface. So that was one hypothesis. The second hypothesis is that the lower valences that are there in the titanium and niobium spectra are due to the accumulation of free carriers at the bottom of the STO film, which screen the transition metal cations that have their nominal charge for that lattice. Well, in order to address these hypotheses, we need to first of all have suitable core levels from each material to try to analyze to extract the potential profiles. And then that raises another question: how in the world are you going to do that? Because we're talking, when we're looking at hard X-ray XPS, we're looking at a lot of layers, and doing it kind of manually like we did for the LSFO on STO is just not happening. It'll take you the rest of your life. So what we did was to develop an algorithm that would allow us to extract the band edge profile from the heterojunction spectrum. And in outline form, the way this works is the following. For each layer in the heterostructure, we assign a reference spectrum that's measured for the pure material in a flat band state. We assign that spectrum to each layer. We attenuate it according to its depth. And so we start off with a family of spectra like that, all at the same binding energy. We then use a random number generator to generate a random binding energy shift for each layer, and we assign those, and then we sort the binding energies from highest to lowest. In other words, we sort the distribution of binding energy shifts, so the binding energy is changing monotonically with depth, either one sign or the other, and we actually check both signs on the gradient of the potential. And the reason we do that is because we know that for a built-in potential, it's going to be a monotonic function of depth. We then, having assigned those monotonically changing binding energies, we add up all the spectra and we fit that to the measured spectrum, and we calculate a cost function, W. And this cost function has two terms in it. The first term is a fit, it's a spectral fit. It's an indication of the goodness of the fit of the simulated spectrum, which is the sum over layers, to the actual experimental spectrum. That's W1. W2 is a measure of the smoothness of the changing potential with depth. That should be a smooth function of depth. And so we vary P in a systematic way, which is the weighting factor on W2. We vary that in a systematic way so that we can tune for smoothness in the potential without losing the quality of our fit. So we do the fit, and then we jiggle the binding energies again, and we resort, and we recompute W, and we keep doing that again and again and again until we minimize the total cost function. What we end up with then is a family of spectra, which when summed gives an excellent fit to the experimental spectrum, like that. And from that binding energy profile, we can extract then a band edge profile by just offsetting it by a constant energy difference between the core and the top of the valence band to get the band edge profile. Now, if we do that for the silicon 2p and the titanium 4+ component of the titanium 2p 3 halves, what we get is shown here. You can see on the right, the quality of the fits is really good. And on the left, you see a heat plot, which shows the intensities for all the different layers, which when summed together give you that best fit over on the right. And then from those, we can, from those core level profile, binding energy profiles, we can extract the band edge profiles for the system. And that's what we get. And so notice several things. First of all, the valence band maximum in the silicon climbs above the Fermi level right at the interface, which explains the formation of the whole gas. Also, the conduction band minimum of the STO climbs above the Fermi level right at the surface, which explains the surface depletion. The valence band offset is easily gotten. We just take the difference in potential between the silicon valence band maximum and the STO valence band maximum, or we could do it for the conduction bands as well. We just take that difference right at the interface, and we find that we have a what's so-called type 3 or broken band alignment with those band offsets. If we take a look at the magnitude of the built-in potential from the photoemission, blow up that region right at the top of the silicon layer, we get 0.98 from the photoemission, and we get 0.9 from the Hall, which is pretty darn good agreement. Also, we know that the electric displacement needs to be continuous across the interface, and we can use that to solve for the dielectric constant in the STO just by taking the gradient of the potential in the silicon and the STO and then the dielectric constant of silicon. We get a value of 30, which is right in the ballpark for what other people get when they try to measure dielectric constants for STO grown on silicon. So that's kind of a sanity check. And I don't have time to tell you about it, but basically this band edge profile has passed all of the other tests we can put it through. We've put it through rigorous tests by modeling the electronic structure of this material in different ways, and it passes all the tests with quantitative success. And the last thing I want to point out is that you notice that in the STO, there's this strong downward band bending, which means that all of the free carriers in the STO are going to accumulate at the bottom of the film, and there are going to be enough of them that they're going to screen the titaniums and the niobiums down there and make them look like they have a lower valence than what you'd expect based on their nominal valence on the lattice. And so that explains the weird looking spectra for the titanium and niobium. All right, so that brings me to the end. And so takeaway messages would be that there are several different physical phenomena that determine XPS line shapes and binding energies. And if you're not aware of them, it can lead to incorrect spectral interpretation. Key things to remember, XPS is a many-body interaction, and that's the best way to think about the binding energy. It's really the difference in energy between the ion and the atom. The X-ray absorption process transforms the entire atom from one state to the other. That involves all of the electrons, not just the one that's core ionized. And then these 5 different effects can all have an effect on XPS. And so that's actually, even though it seems like it's making life complicated, it shows why XPS is such a great source of information on a variety of materials. And a shameless plug here, but I'm preparing a book on methods of epitaxial film characterization for a larger book series with World Scientific. And I've also written a chapter for that book on XPS. It's coming out hopefully later on this year. And so if you're interested in a book on materials characterization for epitaxial films, and if you'd like to see more on my take on XPS anyway, it'll be there in that chapter, which you can hopefully get later on this year. So thanks for listening, and happy to take any other questions you may have.
All right, perfect. Thank you very much. So let me add just another a little bit of a pitch. You also recently wrote one of the guides to XPS spectroscopy for publication in JVST, and there's been a very large series of these guides for best practices for understanding and fitting photoelectron spectroscopy data.
Yeah.
And so I think yours was one of the earlier ones. It may have come out in 2019.
No, it actually just came out in 2020.
Okay, it was 2020. Yeah, so it was one of these series. So I highly recommend these series.
Oh, okay.
And, go ahead.
We wrote two. So one of them came out in 2019, but that was on attenuation links in STO. And the one that I think you're referring to that I co-authored with Don Baer.
Yes, that's the one.
2020. Yeah. Okay.
Yeah, so I highly recommend that series. That's a great series. The other thing is, I think you point out one of the great things, avenues that are opened up by HAXPES, hard X-ray photoemission.
Yeah.
And this is something that I can't wait to put into practice with the HAXPES that we have at Illinois Tech. So we're looking forward to doing things like this at the Advanced Photon Source.
Yeah, great tool. Learn a lot.
So let me ask you a question about the band edge offsets.
Sure.
Do you think it would work with multi-layers? So if you added another layer?
Yes, it does. There is a trick that is really useful, and that is, the problem, if you have multi-layers, the problem is how do you tell one layer from the other?
Yeah.
If your multi-layer sample happens to be a superlattice, you can do something called standing wave XPS. I don't know if you've heard of that variant or not.
Yep.
But that works really well, and I highly recommend that. My group published a paper with Chuck Fadley's group in 2018, I believe, in PhysRev B, where we looked at lanthanum chromite, strontium titanate superlattices. And we were able to, and so for the audience, what happens is if you come in at a certain angle of incidence with your X-ray, then you get an evanescent standing wave that builds up in the material, and you can tune the maxima for the electric field strength in the standing wave to the certain positions in the superlattice by changing the angle of incidence. And so you can selectively photoemit from different parts of the superlattice. So you can emphasize an interfacial region versus phase A versus phase B. And we did this with the lanthanum chromite strontium titanate superlattices with Chuck's group in 2018. And there are a lot of other papers out as well by now where people have done that for other kinds of materials. But that's if you have a superlattice, and you have to make your superlattice with certain dimensions in order to be able to tune it to the standing wave for the X-ray field.
And conveniently for HAXPES, given the geometry of most systems, the standing wave is easy to set up in back reflection geometry. Which is kind of the conditions are greatly reduced there compared to other angles. So it is advantageous for doing that, especially with HAXPES.
Yes.
So let's see. Do we have any other questions from the audience? Nothing at the moment, but no, this is very impressive. It is so hard to basically analyze even some simple systems. Another one that you've worked on that has helped my group out a lot is the silver oxide, where that I think you also did with Professor Bagas. And that is, it's really interesting to me that simple systems like oxides on silver were so difficult to understand and are still wrong in the literature all over the place.
Yeah, it really is crazy. Oxides are complicated, really are complicated. And these effects can kick in, and the relative weight of these different effects, mainly charge distribution, angular momentum coupling, and shakeup. Those three can actually influence one another, and they can couple together to give you final states that are not what you'd expect at all. And it's without first principles calculations, sometimes it's very difficult to know what these things mean. And that frustrates people because they want to just look at the spectrum and say, oh, this means this. And you just can't do that accurately, unfortunately, for some of these, mainly for transition metal containing materials.
Yep. No, it's very hard. Yeah, I like I said, I'm often surprised that it works as often as it does. And we're very fortunate and lucky that it does. But you will find many systems that you don't think are very difficult where you have these odd effects. And so you always have to be on the lookout for them.
Yep, indeed.
And more importantly, you have to know that they exist. Because many people just say, oh, I've gotten this XPS spectrum, we'll just fit it and go about our business and publish it. But you have to be very careful when looking at these things. So,
yeah, well, if you want to end with a good laugh,
yeah,
I'll show you something. You may have seen this, but this is probably the most egregious example of if I can find it, just a major screw up on interpretation. Let's see here. But it illustrates what happens if you aren't careful. Oh, I'm sure I have it in here someplace. Where is it? Maybe I don't. Huh. Oh, no, here it is. Okay. So I will not show that, even though this paper came from a different country, I will not show the authors' names, but it was come on, let's go. There we go. So it was an IOP conference proceedings publication. This was a stainless steel XPS analysis, and it had some aluminum in it. And so there's their survey spectrum. And here's what they did with their aluminum 2P spectrum. And I will let you just take that in for all that it's worth.
All the noise peaks are labeled as chemical components.
Yes.
Yeah, right. This illustrates a huge danger where you don't want to just highlight a database of binding energies.
Yeah, exactly.
It is a very bad thing to do. But yes, it's always good to withhold authors' names to prevent embarrassment. But unfortunately, the sad thing is, to clarify for everybody, this was published. This made it through peer review. So this wasn't in a submission that got caught. This actually made it into publication.
And I think that's what motivated Don Baer to put in the time to get this series of articles together. Is he and Mark Engelhardt are really, they're really, well, they're just committed to having this technique be used well, and so they work tirelessly to try to help educate people. And I understand it's a sort of thing where most of us, we like to have certain techniques in our back pocket that we can just pop a sample in and get out and answer and and be on our merry way. And while you can do that to a certain extent with XPS, it's easy to misinterpret if you are not aware of these different things. And so they just are really keen on helping to educate people who use the technique and to use it as properly as you possibly can, given the constraints that we all have for time and for resources.
No, definitely. And they should be commended for that, because they dragged in a lot of people to help write all these articles, and it was a good thing. And I think it'll help people. At least I hope it'll help people. But
I forgot one thing, Jeff. I forgot to acknowledge all my wonderful collaborators.
Oh, yes, please do.
Let me please do that. That was after my conclusion slide, but this is my epitaxy thin film group down below at PNNL. Wonderful people that I really enjoy working with. And then I have a number of great external collaborators that have been involved in the work I told you about today, mainly the STO and silicon. So Joe Nye, UT Arlington, working on the MBE growth of the STO and silicon. Jim LeBeau did he and his group did the TEM. And then Joe Wojcik, Alex Gray, and Tianlin Li, and James Eblett, they were all very much involved in the Haxpus measurements that we did on these different systems that we've published. So I'm indebted to all these folks a lot.
Oh, definitely. Yeah, no. And let me throw out Joe Wojcik and I were grad students together many, many decades ago, and I was a postdoc when with Tianlin Li when he was a grad student.
Oh,
so,
okay. All right, small world.
People, yeah. So Tianlin is running a Haxpes beamline at Diamond. It's actually one of the best Haxpes facilities in the world.
Yes.
Joe does a lot of standing waves and Haxpes at his beamline at Brookhaven.
Yep.
And so we hope that we'll do as well with our new Haxpes system at the Advanced Photon Source.
Yeah, that's exciting. I heard that was coming together, and I'm anxious to hear more about it.
Yeah, hopefully soon. Unfortunately, we had to send the analyzer back to Sweden, so it had an internal short.
Oh,
so very disappointing, but hopefully they'll get it fixed and we'll be back in business in the not too distant future.
Yeah, good. Well, keep me posted on that once it gets going.
Will do. So everybody in the audience, we thank our speaker by typing applause in the chat window. So if you can thank our speaker, woohoo, let's get those applause out there. Very good. Thank you so much for coming and speaking with us today. And we appreciate your time.
My pleasure. Everybody have a good day.
All right. Thank you.
Okay. Bye-bye.
Bye-bye.